Section 3.1-3.2, Determinants of a square matrix, which is the same as section 3.6 in Edwards. The determinant of a square matrix is a number associated with n by n square matrix whose value characterizes when the linear system AX equals B has a unique solution, or that's the same as saying A inverse exists. So the bottom line is, in other words, any square matrix is associated with a number called its determinant. So the question is, what is a determinant? How do I find it? Determinant of a 1 by 1 matrix is, the element of that matrix. What does that mean? Suppose you have a 1 by 1 matrix, which is 4, 1 by 1. So the determinant of A is 4. Okay, so it's a number. On the other hand, if you have 2 by 2 matrix, all right, so you have what? A11, A12, A21, A22. So that's a matrix, which is 2 by 2. And incidentally, the notation for determinants, the notation or the symbol we use, either we go by DET of a matrix A, or we use absolute value bars. So please make sure you don't use the bars for a matrix. For a matrix, either you use parentheses or what? Or brackets, correct? Because absolute value bars stand for determinant, which is a number. So by definition, the determinant of a 2 by 2 matrix is product of the main diagonal elements minus the product of the what? Off diagonal elements. Case in point, suppose I got 2, 4, -1, 5. I was asked to find the determinant of A. So the determinant of A by definition is 2 times 5 minus 4 times -1, which is 10 plus 4, which is 14. So we got that. But how do you find the determinant of a 3 by 3 matrix? Yes, you can memorize this horrendous formula, which goes from here to here. I don't recommend it. But this is basically the notation, or you could also use this good old notation of DET of A. But the methods we use to find the determinant of a matrix are as follows. One of them is the definition of determinant. We are not going to go over that. It's a very complicated definition. The other method is what? Cofactor expansion, which is easier than the definition, of course. It's called cofactor expansion method. And the other one is called upper or lower triangular form of that determinant of A. Upper triangle means what? Anything above the main diagonal element in the what? Determinant of a matrix are non-zero what? Elements. Anything below happens to be 0. So this is called upper triangular, whereas lower triangular would be what? So this is A11, A22. Let's say we got 3 by 3 determinant. Everything above this guy would be 0. Below this guy would be what? Bunch of numbers. So this is called lower triangular what? Form of a determinant. So cofactor expansion goes as follows. What we do to find the determinant of a square matrix, we first select a row or a column of our own choosing. In other words, select your favorite row and column and do the expansion about. So what you do, once you choose your favorite row and column, you have to multiply each what? Element in that row or column which you selected by its cofactor. Cij stands for cofactor. So Ci1 is like the cofactor of the element in ith row, first column. And then we're gonna what? Add those what? Results up. In general, the cofactor of, let's say, element, cofactor of element Aij, which means the element which is in what? Ith row, correct? And jth column is equal to -1 to the power of I plus j. So this guy is going to generate plus or minus sign times the minor. So this guy is called the minor of what? Of Aij. So what's a minor? Well, minor is going to be a what? Determinant, correct? Of element of ij is the determinant of A obtained by deleting the ith row and the jth column of A. So, as I said, the notation is either det of A or absolute value bars. Let's take the idea home by doing an example so you guys can see what I'm talking about. Suppose you have this 3 by 3 matrix, and the idea is find the determinant of the matrix using what? Cofactor expansion method. So you may select any row or column of A to apply the what? Cofactor expansion method about to find the determinant. Suppose we selected row 1. Say I selected this row to do the cofactor expansion. Remember, I have a choice of selecting any row or any column to apply this formula. You know, the formula of cofactor expansion. So here's what you do. Well, first you list the elements. So let me literally do this problem so you guys can see the problem in action. Sorry about that. So suppose I have matrix A. So what is it? -8, -1, 4, 7, -3, -2, 0, 6, -2, correct? So suppose we select it, so select row 1 to what? To do what? The expansion about, you know, the cofactor expansion. So I'm going to choose row 1. So I'm going to go, okay, determinant of A equals -8, 7, 0, correct? Now, I'm going to what? Multiply these guys by, remember that factor of -1 to the power of I plus j. Instead of using this formula, remember this will work all the time. Start with plus sign and then alternate the signs. So this would be negative, positive, negative, positive, positive, negative, what? Negative, positive. So those are called cofactor expansion signs. Where does the positive come from? According to this formula, this guy is in the first row and first column. So this would be -1 to the power of 1 plus 1 because I is the number of rows, you know, j is the number of columns. So if you're trying to find the factor of what? -1 to the power of I plus j, so that would be first row, first column, so -1 to the power of 2, that gives you +1. So the answer is positive. How do I get negative out of this guy? Well, according to the formula, what do I have? -1 to the power of I plus j, but this is in what? Second row, third column. second row, third column. Raise that guy to the power of 5, and lo and behold, you get a negative. So that's how those signs work. So they are independent of the signs of the element themselves. So you need to insert those next to the elements. Okay, like so. Remember, that has nothing to do with the sign of the element itself. Now, I like to multiply these guys by their minors, which happens to be a determinant. If you started with what? 3 by 3 matrix, the minors would be what? 2 by 2 determinants. Do you see it? On the other hand, if you started with 4 by 4 matrix, the determinants will be 3 by 3, and so on and so forth. What are the elements of this determinant? Well, according to the rule, you're supposed to what? Delete, let's say I want to know the minor of -8. So delete the row and the column which that element is located and see what's left. These guys will be the element of the first determinant, which in my case is what? -3, 6, what? -2, -2. So this is called minor. What would be the minor of 7? Eliminate the row and the column 7 is located or positioned and see what's left. What's left is what? -1, is that right? 6, what? 4, -2. Is that right? And what would be the minor of this guy? It really doesn't matter because I'm multiplying by 0, but just for laughs and giggles and see what would be the determinant minor of what? 0, which is what? -1, -3, 4, -2. I know hopefully how to what? Evaluate 2 by 2 determinant. Remember, you kind of go like a loop. So multiply the what? Main diagonal elements, subtract the product of the main diagonal elements from it. Positive times negative is negative. This guy is what? +6 minus -12, which is +12. -7 times 2 minus 24 plus 0. That's okay because that guy goes to 0. I don't care what that guy is equal to. So this would be -8, correct? Times 18 minus 7, -22. Is that right? So what would I end up with? I would end up with what? Oh, -8 times 18 minus 7 times -22, which is -144 plus 154. And that would be like what? 10. So that would be the determinant of that matrix. Some of you may know a shortcut. I'm sure you do. So this would be a shortcut which only works for what? For 3 by 3 determinant. Remember, do not apply this for any other dimension of a matrix. So suppose I was asked to find the determinant of this 3 by 3 matrix, like so. What you do, I'm sure you know, copy the first 2 columns, like so, and then diagonally multiply these guys as you go up, subtract the results. Okay, and when you diagonally multiply going downwards, add. You see what I'm talking about, right? Let's do the downwards, so that's what? 6, that's 48 minus. This guy is what? 7 times 6 times 4 plus, what is that? 0. And now up. That's also 0. Then you got -2 times 6 times -8. Remember, there is a minus because we're going up. And there is a minus -2, -1, 7. and this is also a minus, and God willing, we should get 10. So there you have it. So diagonal, copy the first two columns, and then when you multiply diagonally, downwards is positive, upwards you subtract the results. Do you see it? If you haven't made a mistake, or I haven't made a mistake, I hope, what you do, you should get the same answer which we had by doing it the formal way. But this is just a shortcut. So the idea is what if I have like, say, 4 by 4? Well, if you have 4 by 4 and you're trying to what? Use the cofactor expansion, take a good look at the determinant and see which column or row has most number of zeros. That would be your best bet when you what? Do evaluate or find the determinant of the square matrix using cofactor expansion. You can't use the shortcut because this is 4 by 4. So what you do, look at the column and or a row. In other words, select a column or row which most number of zeros in it. So that way, when it comes to using cofactor expansion, 0 times whatever is 0. So in this case, your choices are either use column 3 or row 4 because they have most number of zeros. Do you see 2 zeros here and 2 zeros there? So in this case, I have selected row number 4. So what I did, I listed what? Elements of that row, namely 1, 0, -2, plus. But remember those hidden signs from cofactors? They get to be written next to what? The elements. So these are red signs. Those are the cofactor signs. Be careful, right? They have nothing to do with the sign of the element itself. So then what happens is the minors, when I delete, let's say, this row and that column, which one is located, I get a 3 by 3 what? Determinant. So now I continue this on, but anytime I have a 0 element, these guys go to 0 land. But now the question is, how do I do this? Well, to do that, now you have to go back and apply cofactor expansion for what? 3 by 3 determinant and evaluate these guys. For instance, to do this, notice I have what? Applied the cofactor expansion, just like previous example. I got 16 for this guy, and I got 15 for this guy using the previous what? Example. So when you do what? Multiply each element, including the cofactor sign, by their minors. In this case, the answer comes up to 14. Yes? Now, there is a nicer way to do the determinants, but that requires knowledge of what? Properties of the determinants, correct? So this is a little bit lengthy properties, but let's quickly run this by and see if we can remember it for future computations. These are called properties of square matrix, the determinant of a square matrix. If matrix B is obtained by permuting, permute means switching, so this means switching what? 2 rows or 2 columns, then the determinant of the resulting matrix is minus the determinant of the original matrix. In other words, if you switch 2 rows or columns, then you gotta attach a minus to your answer. If B is obtained by multiplying any row or column by scalar k, then you gotta multiply the original matrix by that scalar k. Remember, you multiplied a row or column by a scalar, by a real number, then the answer is going to be whatever the determinant of A is times that number which you decided to multiply a row or column by. On the other hand, if you multiply that, what? The entire matrix A, meaning every element in A by k, then the result will be k to the n times determinant of A. So you're going to have this factor as opposed to this factor if you just multiply a single row or column by a constant. If you decide to multiply the entire what? Determinant by what? By K, a constant, then that will put a dent in your what? In your final answer. If B is obtained by adding a multiple of any row or column to a different row or column, the determinant does not change. So no change here. So if you take a multiple of any row or column of a determinant and add it to a different row, no changes. Determinant of A transpose is exactly the same as determinant of A. If A has a row or column of 0, then the determinant is 0. If two rows or columns of A are scalar multiple of one another, determinant is 0. Determinant of A inverse, this is really important property, is 1 over determinant of A, provided determinant of A is not 0. In other words, provided A inverse exists. The determinant of A times B is determinant of matrix A times determinant of matrix B. However, this property does not apply to plus or minus operations. The determinant of A plus or minus B is not determinant of A plus or minus determinant of B, is not. So the next idea is this. If you somehow, using those, what was it, 9, well, let's finish the properties and I'll show you what I mean. If A is an upper or lower triangular matrix, then the determinant is what? Can be obtained by product of the main diagonal elements. In other words, remember what the upper and lower triangular matrix was all about. These guys. So somehow, not the matrix, but the determinant, if you can somehow put the determinant in either of these forms, the determinant is what? Is the product of the main diagonal elements. In either case, either you put the determinant, not the matrix, but the determinant into what? Upper triangular form or lower triangular form. Then the determinant of these type of matrices happens to be the product of the main diagonal element. And in the land of mathematics, product is shown with capital pi. So that would be pi, kind of product of AII, where I goes from 1 to n, all right? If the matrix, original matrix is invertible, that means A inverse exists, then the determinant cannot be equal to 0. And it works the other way around because this is IFF, which means it works both ways. If the determinant of a matrix is not 0, A inverse exists. So as a matter of fact, this is a fantastic way to see if an inverse of a matrix exists or not. Check its determinant. If it is not 0, it exists. If it is 0, it doesn't exist. It also tells you what? Whether a homogeneous, non-homogeneous system of equations, so remember B is not equal to 0, has a unique solution or not. Check the determinant of the coefficient, matrix of coefficient, and make sure it's not 0. If you have a homogeneous system of equation, that means you got nothing but zeros on the right side, and the determinant comes up to 0, determinant of the matrix of coefficient, you have infinite many solutions. Okay, do you see it? Finally, the determinant of identity matrix is 1. And the determinant, one more, I suppose, A to the power of K is determinant of A to the power of K. So there are 15 properties. It would be nice to kind of remember. So let's finish this section up by putting this, not matrix, but the determinant into either upper or lower triangular. So we don't have to use what? Cofactor expansion method or any lengthy method that we know from other classes. So here it goes. So suppose we change the determinant of A into an upper triangular matrix. Upper triangular matrix meaning you have the main diagonal element and you got numbers here, but you got 0 at the bottom of the main diagonal elements. So here's the matrix. Look what I did. I took R1 and added R2, placed the result in R2 to get a 0. Then I took twice of R1, you know, that's kind of like leading one, remember? And added twice of this added to R3 to get 0. Now, wait a minute. This kind of sounds god-awful like row operation form, but you gotta, what? Keep these 15 properties in mind. One of the properties was this guy. What was it? Was this guy. If B is obtained by adding a multiple of any row or column of A to another row or column of A, then the determinant does not change. So here, I'm taking a multiple of one row and I'm adding to a different row. Therefore, no changes in the what? In the determinant. Otherwise, notice, be careful. If you switch two rows, you gotta attach a minus. You multiply a row or column by constant, then the final answer should be multiplied by k. If you multiply the entire matrix by k, then the final answer has to be multiplied by k to the n. So these are the ones which you gotta watch for. So although it looks like I'm doing row echelon form, elementary row operations, but in back of my mind, I'm thinking of properties of the determinants. Be careful not to mix these two guys up. All right, one more. So I'm going to make this guy 0 by taking negative twice of R2 added to R3. Once again, when you multiply what? Add a multiple of one row to a different row, that doesn't really put any dent in your what? Determinant. The determinant is unchanged. Now that this guy is in what? Upper triangular matrix, so the determinant simply is the product of the what? Main diagonal elements. 1 times 1 times -3, -3. It should have given you the same answer if you would what? Put the determinant, not the matrix, the determinant into what? Lower triangular matrix, and that would give you exactly the same what? Answer. So, but keep in mind, when you do these operations, make sure you put the properties of the determinants on the side to make sure that what? Does that operation which you apply to the determinant put any dent in my final answer? If it does, and you didn't adjust the answer, of course your answer will not come up the same. But let's hope you would apply the what? Elementary row operations by keeping the properties of determinants in mind so you can hit the correct number, not the incorrect number. Thank you, guys.